Okay, so in this video, we're just going to address some of those, confusing things I got not messed up, but just some of the things that may be confusing to you with regards to projectile motion. We're not really going to redefine anything. It's all the same thing, right? A projectile is an object when launched into the air affected only by gravity, right? So it's just some always constant values, right? You always know that acceleration in the x direction is 0, right? Which tells us that our initial velocity will always equal the final x velocity. And AY is always going to be that g value, which is negative 9.81 or negative 9.8, that you can sometimes round to 10. Okay? And so you can plug those into the equations and write a horizontal and a vertical side. We'll do that here in a second. But when it comes to projectile motion, right, we have basically two types of questions. Okay, we have launch horizontally, which I like to call cliff problems because that's what it looks like. All right, and then we have launch at an angle problems. Now, in this category, there are two more, right? When you have an upward angle, and you have a downward angle. Okay. Here, with the upward angle, your initial y velocity will be a positive number, and here with the downward angle, your initial y velocity be a negative number. Okay. Now the downward angles look very similar to the launch horizontally because it's almost like it just falls off of the cliff, but now you're introducing this downward angle. Okay. But those are the types of problems. Okay. Now again, you can do different things, especially with the upward angle ones. These are not. Put asterisks, right? So I can launch from my height, which means it's kind of like if I'm a golfer, I'm launching from a tee box that is above the hole, right? Or I can launch to a height, okay, which is like again, if I'm a golfer, I'm now hitting up to an elevated tee, or excuse me, an elevated green. Okay. When it comes to the launch horizontal, the height sets the time. Okay. That's important to know. Okay. Is that the height is going to set the time for the fall. Okay. It's not necessarily the horizontal velocity, but it is the height. Okay. Now, when it comes to the upward angles, to find times, and when you launch from a height, and the third type can be from the ground. Can go ground to ground, right? These are the easier of the three problems, okay? Because when you go ground to ground, you can just simply treat it as if it was a parabola starting at the origin and going out to a specific time. When you launch from a height, launch to a height, you're probably going to use the quadratic equation to find time, all right? Much like here on the downward angle, you're going to use quadratic equation also to find time. Okay, so you can use that quadratic equation to find time. But we'll go over that. I'm going to do some videos focusing on some of the problems. This is just some general information. Okay. Now, when it comes to the formulas, what you're going to want to do is you're going to want to write horizontal and vertical, okay? Because what we can do is we can break all those equations, those kinematics equations that we've spoken about, we can break them up into horizontal and vertical and really write down, so we call this formulas and givens, right? Things that we can plug into our equations now to simplify, right? So let's start with the velocity formula. So Vx equals Vox plus Ax t. Well, the great thing about projectile motion is that Ax is equal to 0, right? And so all this equation boils down to is that it tells us that the initial velocity is going to equal the final velocity, okay? So that's very important. Okay, that's the first one, right? So that's not good. So the initial velocity, so there's the mathematical proof that the initial velocity equals the final velocity. The other key equation is the quadratic equation, right? The position function. So here it is, x equals xo plus vot plus 1/2 axt squared. Again, ax is 0, so this whole 1/2 axt goes out, axt squared. And we're going to call our initial position 0. So what you see is that this equation just breaks down to be Voxt, right? Because there's no acceleration, it just simply becomes the initial velocity times time, right? Just our basic position equation. Now is when we're going to go to some of the, fun part in the y direction, okay? So remember, AY is equal to negative 9.8, okay, or you can call it negative 10. I'll write the equations with negative 9.8. So what I'm going to do is I'm going to take that AY and plug it in here, and so I end up with VY equals VOY minus 9.8 T, right? And so what we're really doing is just breaking down these equations, and then I'll give you the strategy, okay? The next function, right, the next important one is the position equation, just like we did in the x direction, okay? And here's the thing about this one. Right now, you can't get rid of anything, right? And you have to address this specific question, okay? Because it changes, right? If I'm launching horizontally, all my VOYs would go away. If I'm looking at the maximum height, my VY would end up going away. But these are, so what I highlighted there in pink are the 4 formulas that you need to do, okay? Now, if we look at what is the strategy to solve these problems, really it's 3 steps, right? Really 3+, because that third step is going to have a bunch of steps depending on how many parts that you have to solve. Okay. Okay. Step 1: resolve initial velocity into components. We talked about this when we did vectors, right? We're going to use our trig to break that vector apart, okay? And easy enough, Vox is going to be VO cosine theta. VOY is going to be VO sine theta. Okay, and as long as it's written from the horizontal, or the angle is given to you horizontal, that's what you're going to use. Okay, step 2, write the position functions. Okay, when you write the position functions, you are now setting yourself up to be able to solve for anything you're looking for. Okay, so the position functions are the x equals Voxt, and then you have this quadratic, right? These are the 2 position functions. Okay, so kind of like what I did above where I wrote the equations, you can split your page into a horizontal side and a vertical side. Knowing that, right, if this is a barrier, right, the line between them is a barrier in your key chart, the only thing that can cross the barrier is time, okay? Time doesn't know a direction, and time doesn't care about the direction. It just cares that you started a stopwatch and you're ending a stopwatch, okay? And then finally, the last step is to now solve for what you're looking for. Okay. Now keep in mind, if you're looking for time, you may need to use the quadratic equation. Okay, especially situations when you have angles involved. If it's not ground to ground, if it's not going from, if there is a vertical displacement, this is where you would use the quadratic. Okay, so if I have a vertical displacement, that is now my quadratic equation. Okay, that's where I'm going to do that. Okay, if not, if you don't have a vertical displacement, you can just treat it as if it was a parabola for math class. Okay, especially if you take in Algebra 2, where you spend a lot of time doing parabolics. All right. Now the next group of videos, all I'm going to do is I'm going to look at a bunch of the problems that we did in class, okay, and just kind of redo them so that you have videos of them so you can go back to refer to. And I'm also going to go over the questions that I did not go over in class.